Before you watch this video, please watch the last video which we have created on the CAN. Then you will understand this video better. So we were discussing about the CAN system, and we were discussing why the single wire CAN and the two wire CAN exist and what are the different advantages. So we were on the two wire CAN system. So let's try to understand by that example. So we discussed till here. So here we have the two wires, one is CAN high wire and one is the CAN low wires. On CAN high wire we have the 3.5 volt, and on CAN low wire we have the 1.5 volt. As earlier also I told you that all the data transfer in the form of voltage. Now once these voltage goes to the transceiver, then we have the differential amplifier which make the difference between this voltage, which calculate the difference between the voltage on CAN high and CAN low. So CAN high we have the 3.5 and CAN low it is 1.5, which is coming the 2 volt. This 2 volt means this is the active and the logic level is 0. You can see here, this is logic level 0, and this state is called as dominant state. The possible signal level at different amplifier the output, so either you can have 0 or 1. So whenever logic level 1, then it means that ideal, the state would be the ideal and voltage difference would be the 0 volt. I hope you got what we are trying to say here. But you will be having one question, why you are keeping 2.5 volt as a reference or common mode? Why you are not keeping the 0 volt, right? So you have the 0, then you have 2.5 and you have the 5 volt, right? Sorry, you have the range from 0 to 5 volt, right? So why you are keeping the 2.5 volt as a common, right? Why you are not keeping the 0 volt? So let's try to understand the reason behind this, that why we have 2.5 as a common voltage, not the 0 volt. We have seen the trans receiver how it calculate with the differential amplifier. So but before the differential amplifier, the what would be the condition? This is your 0 volt, this is 1.5 volt level, then 2.5 level, and then 3.5 level, right? It is the CAN low signal when it is on 2.5 volt and CAN high signal when it is on 2.5 volt. So the difference would be 0 volt, which we have seen earlier. But when CAN low signal is going to 1.5 volt and CAN high signal is going to 3.5 volt, then your difference would be the 2 volt. So this is what it has been shown. Same signal at the differential output, it will become 0, and here it will become the 2 volt. This is the output signal. Okay. So keeping CAN high, CAN low centered around 2.5 volt instead of 0 volt allows the transceiver to operate safely in the middle of its voltage range, giving the room to move both up and down to observe the noise spike. We will see here. So if the x is the noise spike, then how it will differ. Okay. So suppose if you would have taken 0 volt and you have some noise spike, then there is no headroom to operate this. Okay, so let's see in the trans receiver operating range. So trans receiver typically powered by a 5 volt supply as we discussed, and sometimes 3.3 volt also, but standard is typically 5 volt. If you centered the bus at 0, okay, at this position, then what will be, you would only be able to pull up, no headroom the below. You can only see the up range but no below range, because our voltage supplies lies within the range of 5 volt. Centering at 2.5 volt allows CAN highs go up to 3.5. So suppose any noise which is generating till 3.5, it can be accommodated, right? CAN low to go down till 1.5 volt. This ensures both lines stays within the linear range for the internal amplifier and comparator of the trans receiver. That is the reason. So if you see here, signal with disturbance pulse before the differential amplifier. So when you have the disturbance of x, so what will happen here? This x signal will make it down, and this also here it will make it down. But suppose if you are using 0 volt as a mode voltage, then there won't be any headroom to go below this range, right? If you see on the same signal, on the clean signal at a differential, because we are not taking the absolute value, so this particular voltage difference will remain same. That is the interesting thing. So if you see 2.5, 2.5, so this will be 0. There is no problem. But when you go with the differential signal, so 3.5 minus x, 1.5 minus x, it will always remain same 2 volt. So I hope you understand that when we are using the differential signal method and you have the noise of factor x, then your differential output of differential amplifier is not changing. It remains same. So if you see, the noise immunity in the two wire CAN system is higher compared to the one wire CAN, because there you do not have the second wire to give this type of arrangement. So the standard which CAN system is complying here, that is 118982. This is the standard. So this standards, what it defines, the recessive state CAN high, CAN low is 2.5 volt typical. Dominant state CAN high would be 3.5, CAN low would be 1.5. This is the standard. Okay, but we have seen that when you have the noise with the X factor, then there is no difference which is coming on the output of the differential amplifier. It remains same. It will be 0 only, and it will come under the 2 volt. So staying centered around the 2.5 volt ensure the compatibility across the ECUs, suppliers and trans receivers. I hope you got the point. If you keep any other value, not 2.5 volt, then what will happen? Suppose if you are keeping the 0 volt, then you will not be having the headroom to go beyond this, right? But when you are keeping this value 2.5 volt, then you can go till here 3.5, you can go till here 1.5. I hope you understand. So what are the different reasons? So first, noise handling. This allow both upward and downward swing to absorb the noise. Trans receiver range operates safely within 5 volt logic power supply. So this is also one of the reason that your power supply can work around the 5 volt logic. Then ground shift tolerance reduces the effect of voltage difference between the ECU. Differential balance keeps signals symmetric for the better signal integrity. So you can understand that when you are using the 2.5 common mode voltage and two wires, then it is very easy to handle the noise. It is very easy to capture that noise. We will see one example when you are using the one wire CAN system and when you are using the two wire CAN system, then we will see that if noise is coming in between the one wire CAN system, then how weirdly it affects. I will discuss this later, the reason behind 1.5 volt and why we are using logic 0 for the dominant, why we are using 1 for the recessive. Okay, all these things we will see in the other video, but let's first understand these two cases. When you are using the two wire CAN, we have the standard 118982. The physical layer, two wires, CAN high and CAN low. Differential signaling, I hope you understand now that what does it mean. Differential signaling is nothing but the voltage difference is taken by the differential amplifier, and on that particular differential voltage the decision is made. Then ideal or recessive state both at 2.5 volt, then dominant bit CAN high rises to 3.5 volt and CAN low drops to 1.5 volt, and differential voltage is 2 volt. So what is the noise immunity? That CAN receiver looks at the difference of the CAN high minus CAN low. Any common noise plus 1 voltage from the EMI shift both wires equally and the voltage difference remains unchanged. This is high immunity against the noise. We have seen this case earlier. Now we see the same case in the single wire CAN, how it will affect. So single wire CAN, you have the SWCAN, we have already discussed. This was developed as a GM LAN. Then physical layer, only one wire is used, CAN single line. Then ideal recessive stage 2.5 volt, dominant bit driven high 5 volt or low 1.5 volt depending on the implementation. No differential pair, only absolute voltage level is detected. Only absolute voltage level is detected, and we will see in this case that what is the issue is coming when you are taking the 0. So any noise directly shift this voltage since there is no opposite wire to cancel. For example, if recessive is on 2.5 and dominant is on 5 volt, and you get 1 volt of noise or EMI, then what will happen? Recessive shift to 3.5 because 2.5 was already, and dominant will shift to 6 volt, right? Margin between recessive and dominant reduces from 2.5 volt to 2 volt. If EMI is strong and receiver misinterpret a recessive state as a dominant, and message will be corrupted, right? So one example we will take. So ECU try to send this 0x123 again. Bit sequence is transmitted as a single wire voltage. 2.5 is recessive and 5 is the dominant. Suppose 1.5 volt transit noise occurs. So what will happen? 2.5 will become 4 volt and dominant 5 volt will become 6.5. The receiver threshold is only 3.75. Now what recessive bit looks like a dominant? This bit looks like a dominant because it went above this 3.75. So this will be a bit error, and final received message could be wrong CRC and corrupted frame message. So this is how this noise will affect when you are using only single wire. So if your noise is very high, like 1.5 volt transient noise, then this recessive state will become the dominant state because your receiver threshold is 3.75 volt only. So I hope you understand why we are using the 2.5 volt as a common mode voltage, why we are using the two wires in CAN, not the single wire. Data rate is also one of the reason, because in single wire you can take till 33.3 kbps. And if you see the technically also, that how this high immunity against noise work in single wire and the two wire. Just to give you one final difference between two wire CAN and single wire CAN by this table. These are the parameters which are listed here, and two wire CAN ISO 11892, this is the standard which we are using, and single wire we are using the 11893, or you can say GM LAN or SAE J2411. So wire use CAN high and CAN low. We are using the differential signal. Only single wire. There are two states: ideal, recessive, both 2.5. Single wire 2.5. Dominant state, CAN high would be on 3.5 volt, CAN low would be on 1.5 volt. Voltage difference would be 2.5 volt. But in single line, pulled up high will go to 5 volt and pulled up low will be go to 2.5 volt. That noise immunity very high, common mode rejection, and very low absolute voltage detection. So this works on absolute voltage 5 or 2.5. Then data rate up to 1 Mbps, and typically here you have the 33.3 kbps. Here the typical use for the high speed ECU networks which we have discussed, and here low speed body networks. This is the overall explanation of the single wire CAN and the two wire CAN. If you want to understand that why we are using the logic 0, logic 1, dominant state, recessive state, how it is working, why we are going till 3.5 volt only, 1.5 volt, other typical values, please comment in the comment box. I will create the next video on this topic. Thank you for your time. If you like the content, please like and subscribe.